Hi everyone, welcome back. In this video, we are going to take a look at Chapter 2, Section 5 in our textbook, where we look at operations on functions and then also composite functions. So what happens when we put a function inside of another function? All right, so to start off, we're looking at composite functions, and we're going to start by looking at operations between functions. So let's take a look at two different functions. F of x is going to be x squared minus 1, and g of x is x plus 1. All right, so we have two functions here. If we want to perform operations between these, for example, add the two functions or multiply them, we can write that using our letters f and g. So there's kind of like a shorthand way to write these operations. So if we're adding f and g, we can write that as f plus g of x. So instead of writing out f of x plus g of x, we'll write for the function part, the letter part, we're adding f and g. And then to the right, the of x is telling us that x is the input for the function that we get once we add f and g. So here we're just adding x squared minus 1 plus x plus 1. In other words, we get x squared plus x. So here's the notation we're using for adding. Our notation for other operations is really similar. If we subtract, we're looking at f minus g of x. So here, x squared minus 1 minus x plus 1, which gives us x squared minus x minus 2. For multiplying, we have f times g of x. So really similar notation, x squared minus 1 times x plus 1. So here we have x cubed plus x squared minus x minus 1 for multiplying. Finally, we have dividing, where we have f divided by g of x. So any operations we're performing, we'll write in front of the x and kind of like the letter or the function part of the f of x notation. So here, x squared minus 1 over x plus 1. We can actually divide this because we can factor x squared minus 1 into x plus 1 times x minus 1 over x plus 1. And then we end up with x minus 1. And a small note here is that we know in the domain x cannot be equal to -1 because we have a denominator that could be 0. So just a small note with that division. But this is the notation that we'll use when we perform operations between functions. So pretty straightforward how we perform those operations. It's just important that we know what this notation looks like. So if we're given a problem with this notation, we know exactly what to do. Okay, so next up, I want to take a look at composing functions. So function composition is kind of where we plug one function into another function. So one way to think about it, just generally, is that we're taking a function and we're plugging it into the input of another function. And there's a few things to look at. First, we're going to talk about notation. We'll go through some examples, and finally we'll talk about domain and range, because domain and range is really important when we're combining functions in this sense. Okay, so to start off, I want to take a look at the notation that we're using. So we'll start with our definition that the textbook gives us. Given two functions, f and g, the composite function, the composite function denoted, and here we have the two function letters f and g, and then in between them we have a little open circle. So it's kind of like the closed dot that we use for multiplication, except it's going to be open, a lot smaller than like an O, for example. So f composed with g. F composed with g is how we can talk about this notation or this meaning. F composed with g is defined by, so f composed with g, f composed with g, so not fog, just f composed with g of x. So notice we're putting f composed with g in that first part of the f of x notation where we put the letters. is equal to f of g of x. So we're taking the second function and we're plugging it into the first function. So we're taking g of x, we're plugging it into f of x as the input. And then a quick note about the domain of f composed with g of x, or just f composed with g, is the set of all numbers x in the domain of g such that those outputs, g of x, of all those numbers, is in the domain of f. Okay, so what's happening here, and we'll talk about this a little bit more later on in the video, is the domain of the composite function. We need to choose x values specifically so that when we plug them into g and we get an output, that output needs to also be in the input of f of x. And that's because we're taking the outputs from g of x and we're plugging them into f. So if they don't work when we plug them into f, we're going to run into some problems and get some undefined outputs. And again, we'll talk about that in a moment. So here's the definition that our book gives us. Let's talk about what this means, and let's look at a couple of examples. So to start off, we could look at two functions and then find the composite function of those two functions. An example is if we had f of x equals x squared and g of x equals 2x plus 3. We could find f composed with g of x, and we can write it by taking one function and plugging it into the other. So f composed with g of x is equal to, as we saw in our definition, f of g of x. So f of g of x is 2x plus 3. So what we're doing is we're taking our x and f of x and we're replacing it with 2x plus 3. So instead of x squared, we have 2x plus 3 squared. And that is our composite function, f composed with g of x, 2x plus 3 squared. We could also compose them in the opposite direction, so the order does matter. We could look at g composed with f of x. So here we're taking g of f of x, so we're plugging f of x into g of x. So in this case, we have g of x squared, which is, so we're taking the x and g of x, replacing it with x squared. We have 2x squared plus 3. So the order does matter. Notice we do end up with two different functions if we switch the order. So composite functions are just taking one function and plugging it into the other. G composed with f of x is 2x squared plus 3. Another thing we could do is we could look at a function that's given to us, and we could work backwards and try and think about, all right, looking at this function, what two functions could we compose to end up with this function? An example is if we had a function like h of x, some other function, and let's use some of the examples we've been working with so far. If h of x is 2x plus 3 squared, we might be asked to break this up into two composite functions. Composite functions. Okay, and this will actually come up a lot in calculus. You won't learn this until next year. It's not super important. You don't need to know it now, but use substitution is a method of breaking up functions that makes it a lot easier to perform, to do some things with those functions when it comes to like derivatives and other things we learn next year. But use substitution is the name. So it is important that we learn or understand how to break up functions. So something like this, we can see, all right, we have h of x equals 2x plus 3 squared. We could split this up. There are a couple of different ways we could split this up. One way to split it up is to break it apart. We have 2x plus 3 inside of here. So that could be one of our functions, and the other function could be just taking some value x and then squaring it. So the other function is just taking it and squaring it. So for example, we could say here that g of x is 2x plus 3. Here's one function. And then the other function we're breaking it up to is f of x equals x squared. So finally, h of x we could rewrite that as f composed with g of x. So taking g of x, plugging it into f of x. So we can work backwards. And there's usually more than one way to break it up. But this is an example of just looking at it and breaking it up into what's inside and then squaring it. So when we talk about composite functions, we can take two functions, compose them. We can also look at a composed function and then break it up into its individual parts. All right. Next up, lastly, I want to talk about composite functions and finding specific values. So let's consider, before that same notation we had before, f of x is x squared, g of x is 2x plus 3. We might be asked to find f composed with g of a specific value. So we might be asked to plug in a value for 2, f composed with g of 2. We could do this if we already found f composed with g, like we did up here, 2x plus 3 squared. We can just use 2x plus 3, f composed with g of 2 is going to be 2 times 2 plus 3 squared. So we're just plugging in 2. We're plugging in 2 into our x over here. And then solve from there. So notice we have 4 plus 3 squared, or 49. You could also f composed with g of 2. We could also break this up like we did before, where we have f of g of 2. And then f of, well, g of 2 is going to be 2 times 2 plus 3, so 7, f of 7, which is just 7 squared, or 49. So we could also be asked to find the composite function and find specific outputs for a given input of a composite function as well.